So today what I want to talk to you about are Hilbert spaces and their bases. Now, an orthonormal basis is sort of the first thing that a lot of people think about when they think about a Hilbert space. This is what you're trying to find when you take like a singular value decomposition of an operator or a matrix, which is done all the time in data science. And when you think about your first example of a Hilbert space, that's usually L2 of say 0 to 2 pi or something like that. And basically, an orthonormal basis that you could select would be a Fourier series. We're going to prove two different things today. One thing we're going to prove is the existence of an orthonormal basis for a Hilbert space. It turns out that every Hilbert space has an orthonormal basis, and if the Hilbert space is what is called separable, which means it has a countable dense set, then there is a countable orthonormal basis for that Hilbert space. And after we've established that, we're going to take a look at the Fourier series for L2 and show that this is actually an orthonormal basis for L2. And if we have time, I'm going to try to also squeeze in the convergence theory that goes behind this. It is an approximate identity argument, and this sort of argument comes up over and over again in mathematical analysis and functional analysis.
Okay, so I've never tried this projector thing before, but let's see if this works out. My kid's room is the only one that actually that gets dark enough to try this out, and so I'm in here and I have a minion holding my microphone. So let's see how this goes. So here's what's important. We are talking about orthogonal sets. These are subsets of Hilbert space, say V of H, such that whenever we take any pair of X and Y from V, the inner product between X and Y is going to be either 1 or is going to be 0. It is 1 if X is equal to Y, and so it's basically norm 1. And if they are different vectors, then is 0. An orthonormal set here, the classic one that we all know is from Rn. So this is R3, for instance, and so 0, 0, 1, our Z direction, 1, 0, 0, our X direction, and 0, 1, 0, our Y direction. These three constitute an orthogonal set, or orthonormal set, because the dot product between any of these two is 0, and that's because they have 90 degrees between them. They're orthogonal. So that's an orthogonal set. And what can you do with them? Well, we like to use orthogonal sets as function approximators, or a way of expanding our members of H into something else. And so we can do that through the projection and doing that on like a finite set of them one at a time, and then later on build up to that. If you go ahead and take a look, so suppose that we have these vectors E1, E2, etc. going off to infinity, countable, but going off to infinity. We're going to assume that this is an orthonormal set in a Hilbert space H, and we're going to take some arbitrary element F on our Hilbert space. And so what we're going to do is we're going to compute the projection of F onto E1 through En. And when we do that, we already figured out how to do this. So basically, the projection is in the span of these basis functions. And so basically, we have a finite dimensional space spanned by these basis functions, and we're going to have these weights on them. These weights, how do we compute them? Well, we know from the Hilbert projection theorem video I did a little bit ago, is that you need a Gram matrix. And you're going to invert that against F interproducted with E1 through En. And that's going to give you weights. And these weights go here. Now, the Gram matrix is just all the pairwise inner products between your basis functions arranged in this matrix. And you notice anytime we're off the diagonal, we're going to have the inner product between two different members of our orthonormal set. And since they're different, that means that that inner product is 0. And down the diagonal, we have the inner product with themselves, and that means that that's all 1. That's the normality coming in here, which means that this entire matrix is the identity matrix, which means its inverse is itself the identity matrix. So we have the identity matrix times this is equal to W1 through Wn. These W's are just the inner products of F against each one of these E1s through En, which is nice. So that means that basically it takes big O of n time to compute the projection of F onto the span of this orthonormal set, which is really nice. And a lot easier than inverting a matrix. This is what we get. This is how we write it out. The projection of F is equal to the sum from L equals 1 to N of F with EL times EL. Pythagorean theorem basically says that if you take F and you look at its projection and F minus its projection, these two guys are actually orthogonal, so that we can write the norm squared of F is equal to the norm squared of the projection plus the orthogonal complement squared. And so then if we kill this, we get something smaller. Then that means that the norm of F is bigger than the norm of this. The norm here is actually equal to this. And so then this guy is bounded by this. and this is Basel's inequality. And it also tells us that if we take this off to infinity, then we have a consistent uniform upper bound, and so then this will converge absolutely. So that's really nice, and that allows us to have a full expansion going off from 1 to infinity and not just stopping at that n. Now let's see an example of an orthonormal set, something other than Rn, and that is going to come from L2 of, say, negative pi to pi. You think of it as L2 as, or the 2 pi, we just shifted it over a little bit just to be centered. It makes things a little bit easier to express. So if we take a look, so L2, if you remember, is the functions going from minus pi to pi to the complex numbers such that they are square integrable. Then what we're going to be considering is a set 1 over the square root of 2 pi times e to the I n t. This 1 over square root of 2 pi is a normalization constant that is going to end up giving us that 1 later on way down here. So then basically we're looking at these e to the I n t's, and finite linear combinations of these guys ends up giving us what we call trigonometric polynomials. Trigonometric polynomials are these guys. And so if you take a look at the real part of e to the it, you get cosine. The imaginary part gives us sine. And then, for instance, if you take it up to e to the I 2t, then you get cosine of 2t and sine of 2t through the real imaginary parts. So this is indeed trigonometric in a sense. And so it just all comes down to how you combine these guys. Let's show that they're actually an orthonormal set. That's not too bad. What we do is we take a look at n and n prime in the integers, and if they're different, then if we take the inner product between these two guys, we're going to have e to the I n t and e to the I n prime t, and e to the I n prime t comes in here with a conjugate in the inner product. That just flips the sign here, and then we can recombine it into getting e to the I n minus n prime times t. All right, that is something we can actually integrate, so we get this. And so when we compute this, we end up getting e to the I some integer times pi minus e to the minus I times integer times pi. So it is a difference of 2 times that integer times pi. And since e to the I t is 2 pi periodic, this number and this number are the same. That makes it 0. And if n and n prime are the same, then you go through all these computations, and then n minus n actually ends up being 0. So this is just the integral over 1, and that integral ends up giving you 2 pi. So this one up here gave us 0. So we get orthogonality when n does not match n prime, and we get a consistent 2 pi when n matches n prime. If we divide by the square root of 2 pi, then ta-da, we have normalized everything. So this would end up giving us 1. And ta-da, that is an orthonormal basis. Rather, it's an orthonormal set. Is it a basis is actually the big question. And that's what I'm going to be showing you at the end of the video through all those proofs. And so is this a basis? We know we can at least write everything into an expansion in terms of this orthonormal set, but we need to show that this is actually a basis, that this is a complete set inside of our L2 of negative pi to pi. And so stick around, we'll go ahead and show that. But before that, basically an orthonormal basis is going to be an orthonormal set that is also complete. What does complete mean? This is not complete in the sense of metric spaces. This means we're talking about a complete set inside of a Hilbert space, which means that if we take the span of V inside of H, that is actually said to be complete if we take its closure, and that gives us all of H back. What that means is that the span of V is dense in H, or another way to say it is that if we basically take linear combinations of elements of V, we can approximate anything we want in H. We say an orthonormal set V in H is an orthonormal basis if V is actually complete in H. And so that's really what we're trying to show with this L2 of negative pi to pi. We've demonstrated that we have an orthonormal set, but we don't know it's actually complete inside of L2 of negative pi to pi, and that's what we want to show. So what we're going to prove here is that every Hilbert space has an orthonormal basis. And what we're going to use to prove this is Zorn's lemma, which comes out of this abstract algebra book. I guess this really falls underneath logic more than anything else. But what Zorn's lemma does is it basically says that if you have a collection of elements that have some sort of partial ordering, in this case we're going to take a look at all orthonormal sets, and the partial ordering we're thinking of is the subset relation. And if for every chain of subsets we have of these orthonormal sets, we can find some upper bound to all of them, which is actually the union of the entire chain. And if that happens, there must be some maximal orthonormal set. And this orthonormal set, this maximal orthonormal set, actually ends up being our orthonormal basis. So now let's show that this maximal orthonormal set is actually a basis for our Hilbert space. And so what we're going to do is we're going to take the span of the entire orthonormal set, which means all of the finite linear combinations of elements in here, and we're going to take its closure inside the Hilbert space, which means that we now have a closed subspace of our Hilbert space. And if it's a proper closed subspace, then that means that there's an orthogonal complement that has something other than the zero vector. If it has something other than the zero vector, then that means we can normalize it, and it's going to be orthogonal to everything that was inside of that maximal set. Which means if we take that element and we add it to that maximal set, then we have a larger set than the maximal set, and that's actually a contradiction. Which means that the span of our maximal orthonormal set must actually be the entire Hilbert space. And so there you go. By Zorn's lemma, we have thus found an orthonormal basis for our Hilbert space. We know that it is a complete set. All right, so now let's show that trigonometric polynomials are dense inside of L2, which will then show that the e to the int for n ranging from negative infinity to infinity is actually a complete set for L2 of negative pi to pi.
All right, so a trigonometric polynomial is a sort of function that is like a polynomial, except it is in the terms e to the I theta, or e to the it. So you have various powers of e to the it, which is e to the int, and our goal is to show that these are actually dense inside of L2, which means that any sort of function in L2 can be well approximated according to the L2 metric using one of these trigonometric polynomials. But we're going to do this in a kind of roundabout way. What we're going to do is we're actually going to show that these do even better than that, and that they're actually complete inside the space of continuous functions in the sense of the uniform convergence. So if we can show that for every time we have a continuous function, we can find a trigonometric polynomial that converges to that uniformly, that means it's also converging to that in L2. And this works because uniform convergence over a finite interval implies convergence in L2. And since every continuous function can be approximated in this way by trigonometric polynomials within inside of L2, and any element of L2 can be approximated by a continuous function, that means that the trigonometric polynomials are actually complete inside of L2 itself. So that's sort of the route that we're going here. Now, the approach that we're actually taking is actually fairly simple. We're going to be using what is called an approximate identity argument. An approximate identity argument is a very standard thing out of functional analysis, and it allows us to prove the convergence of all sorts of things. We actually use an approximate identity argument when we proved polynomial approximation, the Weierstrass approximation theorem, back when we were talking about stuff out of Rudin. And so I'm not going to go through all the details of the approximate identity argument here, because it's the same exact argument that we used back there. You can go check out that video, but I can show you how we can use this argument to also give us the completeness of trigonometric polynomials. So first, let's identify what an approximate identity actually is. And it is a sequence of functions. And another way to call this is a delta sequence. So I wrote up some notes here, and we see that this is an approximate identity. This is the definition that I'm working on here. And it is a family of functions, say phi n, and we're going to be looking at, say, negative pi to pi here, just because it's nice to have this sort of symmetric over the interval. You can shift anything you want from negative pi to pi to 0 to 2 pi if you want, or rescale it, or all these things. That's all perfectly fine. And so this is a family of functions that, 1, they're always positive. 2, the integral over this interval is always 1. And if you take a look at any sort of the edges of this as they sort of like come in, we're going to be going uniformly to 0. So the only spot that isn't going to be going to 0 is the area around 0 itself. And that is supposed to be concentrating all of our function values there. And we know that the integral from negative pi to pi is 1, and so ultimately we're trying to move that entire area inside of small neighborhoods around 0. So if you take a look at the book Applied Analysis by Hunter and Nottingale, you will see they actually have all of this in there in a bit more detail. And in there, there's this theorem. It's out of chapter 7. It basically says that if you have an approximate identity, and f is a function as a continuous function over negative pi to pi, then the convolution of f with this approximate identity, this sequence of functions ends up converging to f uniformly over that interval as n goes to infinity. And this is a convolution in this case, if you haven't seen it before. And like I said, it's exactly the same proof that we gave for the Weierstrass approximation theorem for polynomials. And in this case, we used a particular approximate identity. Basically, every function that came out of it was a polynomial. And in this case, we're going to pick another one that is going to do exactly the same thing, but it's going to kick out trigonometric polynomials. So the approximate identity we're going to be working with here is defined in terms of cosine. And so it sort of lends to also the name trigonometric series, where basically what we have is that we are saying that phi n of t is equal to 1 plus cosine of t raised to the nth power. We also need to multiply by the sort of cn in order to, quote, normalize it, so that we make sure that the integral from negative pi to pi is always 1. But if you look at this, it makes a lot of sense. Essentially, 1 plus cosine of t is shifted up from the origin, and so we know that that is always at least 0, and usually just positive. As we take this to higher and higher powers, we're going to see that all of that information is going to start being compressed around 0 as n goes to infinity. And so this actually is an approximate identity. And to show that this actually corresponds to what we are calling a trigonometric series with the e to the I and t's, we can go ahead and just expand out the nth powers here. So what we can use is we can use a binomial theorem. And when we use the binomial theorem, we get this. Then you'll see that we can use the binomial theorem again on the e to the I t plus e to the minus I t. And that's going to give us a whole bunch of different powers of e to the I t. And if you organize everything nicely, you can show that this is basically just a sum of powers of e to the I t. And so a trigonometric polynomial. Now what we want to do is we want to take this and we want to convolve it with f. And we want to show that when we do convolve it with f, that the result ends up being a trigonometric polynomial. And then we know, since this is an approximate identity, that this convolution will converge to f as n goes to infinity. And so that means that we're going to have a sequence of trigonometric polynomials that are converging uniformly to our continuous function. Okay, so now what we're going to do is we're going to end up getting a convolution of our function f with this approximate identity, the sequence of functions. And we know, since this sequence of functions is an approximate identity, the convolution of that with a continuous function f does converge to f uniformly over this interval. But the thing we need to show is that the convolution actually is trigonometric polynomials. And so if they are all trigonometric polynomials, then that means that we have a sequence of trigonometric polynomials that are going to be converging uniformly to f, and that's what we're looking for. So the last step here then is to just go ahead and demonstrate that these are trigonometric polynomials that are coming out of this. And so let's go ahead and write that up, and we'll start with just writing out the convolution of f with this approximate identity. So what we're going to do is we're going to take the convolution between, say, phi n and f, and we're going to look at this at the point t. And so this is the integral from minus pi to pi of phi n of, say, t minus tau times f of tau d tau. Okay, so significant here is I made sure to put the taus in the f. I could switch this around by a change of variables and whatnot, but by putting the taus in f, I make sure that all the terms with f are sort of going to become just sort of these constants that we can sort of pull out. And what's going to be left over are the functions that we really care about. So we know that phi n of t can be written as a trigonometric polynomial. I'm not going to write it out the way we had it in the last slide because that's a lot, but it's just basically a bunch of coefficients, say L going from, say, 0 up to n, and we're going to have a n L and then times e to the I L t. So now we're going to put that in for phi, and we're going to see what we get. So now what we're going to do is I see that the t's are actually independent of tau, which means that if I can isolate them as coefficients, I can go ahead and factor them out. And they'll actually just be the terms of our trigonometric series. And so what this gives me then is we have the sum L equals 0 to n of a n L. Now those depend on tau, so we can take those out. And then we end up having e to the I Lt, and this times the integral from minus pi to pi of f of tau e to the minus I, say, tau d tau. And so there we go. This term here is just a constant. And in fact, those are Fourier series coefficients that we had from the projection. This isn't going to be as good as the projection as what we saw before, and that's because we're using these other coefficients, and so this is going to give us a worse approximation. But we don't care about that. We're just trying to prove that this works. We know how to get the best approximation. We're just trying to prove that the approximation, that everything in L2 can be approximated with these. And so we're using this sort of like rougher approximation just because it's easier to work with. Anyway, and so then the only thing that's really a function of t in this case, which corresponds to this guy, is the e to the ILT. And so that makes this a trigonometric polynomial, and we know that this sequence actually does converge to f. So that's really handy. Now, again, if you wanted to see the full proof of how do you take an approximate identity and demonstrate the convergence uniformly, well, I have that in my Weierstrass approximation video from maybe about a year ago, so you can go back and check that. And otherwise, I want to thank you for watching this far. We have now demonstrated that these trigonometric polynomials actually do converge to f. And if you want any of the code from any of the figures that I put together with MATLAB, then you can go ahead and find a link in the description. And I also have a link to the MATLAB Online, which is actually free to use for 20 hours every month. So if you sign up with them, you can just go and try to play with the code that I've been giving you guys. With that, I'm going to go ahead and stop. And, well, thank you so much for watching, and I hope you have a great day.